From Bernoulli's principle, we can derive Bernoulli's equation, which Bernoulli's equation really is the idea of the conservation of energy within a fluid. So what I want to show you first is what does the conservation of energy look like and how we can then convert it into fluids and how we can apply it to a situation as we see here. So the conservation of energy pretty much says that the amount of work plus the potential energy plus the kinetic energy at any given position has to remain constant. We can't add or lose. The work can gain or the work can add to my potential or kinetic. My kinetic or potential can be lost and due to work. But that relationship of those three ideas is going to remain constant, whether it's a roller coaster going down a hill, a pendulum swinging back and forth, your two classic physics examples. So how can we convert these into fluids and understand what that tells us? Well, first off, work is force times distance. If we think about this, what I'm going to do with all of these is I'm pretty much going to get it into a fluid scenario where if we're going to divide by volume of water, right? So when we're talking about a fluid moving through a system, we're talking about a set volume of water here. This is my volume. Looking at this, force times distance, volume would be the area times distance, times the length that I have here. And so from this, my distances cancel out, and we can see that if I take work and divide by volume, I get pressure, because force over area is pressure. So that's the first concept. So work is going to be converted into pressure. Our second idea, potential energy. If we take potential energy as mgh, well, what we've seen in fluids is that mass can be challenging to figure out. But what we can understand is that mass is also based on the density of an object, the density divided by my volume, times gravity times h. So our potential energy is going to now turn into rho g h, where rho is the density of the fluid moving in my system. Kinetic energy is going to be very similar. 1/2 mv squared can be converted by changing my mass into density. So I have 1/2 density of my fluid divided by the volume, velocity squared. And I'm going to get rid of my volume because I have 1/2 rho v squared. What I can do is I've pretty much eliminated the volume in each of these because the volume of water is going to be the same whether it's at position 1 or position 2. And so because this is going to be constant, whatever the sum of them are on the left is going to equal to the sum on the right. And so what I can do is just simply get rid of volumes at all those positions. Putting that all together then, we're going to get Bernoulli's equation. Bernoulli's equation can be written as the pressure at position 1 is going to equal the density times gravity times the height at position 1 plus 1/2 rho v squared. That sum has to equal the same at position 2. The pressure, the potential energy, plus the kinetic energy. And so with this, we can work through problems of, maybe we have to use our flow rate first, and that can help us determine how does the velocity at 1 compare to the velocity at 2. In this situation, we might say this has an h of 0, right? So this is the ground level. So then my height difference, that would be h, right? So in this situation, I'd have no potential energy at 1, but I would now have potential energy at 2. My pressures, because they are in a closed system, are going to be different. In this case, because we have a change in velocity, right? And so I can use this equation to relate anything at position 1 to anything at position 2 and be able to solve for whatever unknown I might have.